Okay, so now we're going to talk about the addition and subtraction algorithms. And what we mean by algorithms is the procedure for computing the sum of two numbers and the difference of two numbers. And if you remember in the introductory clip, we discussed how it's never a good idea just to teach procedures simply by giving students a list of steps to carry out without any meaning behind them. And we can illustrate the reason for that with just a simple addition problem. 46 plus 38. So let's say you told your students a procedure, the correct procedure even, to add 6 plus 8 together and get 14. And that would be step 1 of the procedure. And step 2 of the procedure would be put the 4 here and the 1 here. And then the next step of the procedure would be simply to add in the next column and 84. So if your students remember all of those steps correctly, they're going to get the right answer. But students are going to have to remember a lot of stuff in their times in elementary school, right? And it's very conceivable that if a student is just told a sequence of steps, that he misremembered them in some way, either interchange the steps or just kind of flip-flop some parts of the steps. And what we see often, oops, sorry about that, is that a student could conceivably make the following mistake, where they're remembering the steps correctly, 6 plus 8, 14. But then the next step, perhaps they interchange the actual steps, what they're supposed to do. So 6 plus 8, 14. The student might remember I need to put a 4 somewhere and a 1 somewhere. But again, it is conceivable that the student would misremember where to put what number and perhaps put the 1 here and the 4 here. The problem is such a student is not going to really catch their mistake because they have they have no understanding of what they're really doing. They don't really know what type of answer they should get. They don't know that place value is playing a part here. They're just remembering steps of procedure. They're thinking they're remembering them correctly, and they're going. Okay? So what we want to do instead is motivate the steps of any algorithm. So we want to explain why the steps are what they are. Why do they make sense? Because again, everything in math makes sense. If we follow it from a logical starting point to a logical conclusion, all of the steps in between should build off something that is previously learned. And the addition algorithm can be built upon chip models, what we just talked about in our conversation about place value. Okay? So if we, for example, wish to simply add the numbers 32 and 26, relatively simple addition problem. Let's see how this would happen on a chip model. What would we do on a chip model to add these two numbers together? We recall what a chip model looks like. It's simply a rectangular model that is going to have columns for each place value denomination. And in this case, we're simply adding 32 and 26, so we only need 2 denominations. We need the ones place and the tens place. Now, what we might do if we're teaching an elementary school class this topic, we might do several examples on a chip model before we move over and show how the algorithm is computed. I'm just going to do them in tandem because, again, we can see the parallel nature of the steps that we carry out in the model carry over exactly to the steps that we carry over in the algorithm. So, again, we have to also understand that addition is the act of combining two numbers together to make a sum. So if we wanted to add 32 and 26, then we're going to combine both of these numbers on this chip model together. So 32 again is 3 tens and 2 ones. 26 is going to be 2 tens and 6 ones. And the model alone, we don't really have to do much else to illustrate how we are going to add these two numbers. The model illustrates the two main features of the addition algorithm. And the first main feature is the fact that the way that we add is within each place value denomination. So we're going to add ones to ones, tens to tens, and if the numbers were larger, hundreds to hundreds, thousands to thousands, and so on and so forth. So it's very clear here that, for example, if you have 2 ones and I have 6 ones, then together we have 2 plus 6 or 8 ones. So the first step in this process is simply to add 2 plus 6 together because that's the total number of ones that we're going to have. And similarly, we're going to add, if you have 3 tens and I have 2 tens, the total number of tens we have is 3 plus 2 or 5 tens. It's clear from the model alone that the way that we are going to add 32 and 26 on the model is just to combine the chips together. But on the algorithm, it's clear that we're going to add 2 plus 6 together in the ones place and get 8. And we're going to add 3 plus 2 together in the tens place to get 5. Clearly, this is the simplest type of example because it doesn't involve regrouping. So I mentioned earlier there's kind of two main features of the addition algorithm. And one of them is that we simply, again, add place value to place value, ones to ones, tens to tens, so on and so forth. That's illustrated by the model. And the other main feature of the addition algorithm is the regrouping component. So now let's do an example that involves some regrouping. So suppose we wanted to add let's say 158 plus 76. You can see just from the numbers I've chosen that this problem is going to involve some regrouping. So we are going to have to recall our conversation on place value. And the rule of base 10 that we discussed, 10 of one denomination makes one of the next higher denomination. So we start with our chip model. We are, in this case, going to need 3 place value denominations, 3 columns, one for the ones place, tens place, and hundreds place. Again, we recall that addition is simply the act of combining two numbers together to make a sum. We are combining 158, which is 1 100, 5 tens, and 8 ones, if we think about it in expanded form, with 76, which again is going to be 7 tens and 6 ones. And again, if you were teaching this to a class of elementary school students, you might do several of these on the model first before you step up to the algorithm. I am just going to do them in tandem to illustrate that any step that we carry out on the model can be replicated on the algorithm. This is how the kids are going to understand the steps of the algorithm, by first carrying them out on the model. Okay, so our first step, if we were solving this problem on the model, would be to, like we did earlier, add in the ones place, because we already understand that we have to add ones to ones, tens to tens, and so on and so forth. The issue we have here, though, is if we add up all of our ones, we have more than 10 of them. So now our place value rule kicks in. And we again recall that our place value rule in the base 10 system is 10 of one denomination is equivalent to 1 of the next higher denomination. Now, how we can illustrate that on a model is we can just grab on or put a circle around 10 of these ones and illustrate with an arrow that 10 of these ones are going to become 110. So this is how we can illustrate the regrouping that is necessary with this problem. Okay? Now, how would that step translate over to the algorithm? Well, we would do exactly the same thing. We would just do it without circling chips. Really, all we did over here was we added 8 to 6. We got 14. That's what's going to be done here. We're going to add in the ones place. 8 plus 6 is 14. Now, when we get more than 9 of something, our place value rule kicks in. If you have 14 ones, that's the same as 10 ones, an additional 4 ones. But 10 of those ones becomes 110. That's why this number 1 is put up in the tens place. And 10 of those ones became 110. We have 4 ones left over. That is why we have a 4 in the ones place of our answer. Okay. So again, that exact step on the model carries over to the algorithm. And then we just repeat this step over and over as many times as we need to. In the tens place, we started with 5 tens and 7 tens. We got an additional 110, so now we have 13 total tens. Again, our place value rule kicks in. Anytime we have 10 of something, we can group those together to make one of the next higher denomination. Well, how would that step translate over to the algorithm? It translates just the same way as it did before. In the tens place, we started with 5 plus 7, which is 12. We got an additional 110 from regrouping ones, so now we have a total of 13 tens. But 10 of those tens is equivalent to 1 100 by our place value rule. That's why the 1 goes up in the hundreds place, and that's why we have 3 leftover tens in the tens place of our answer. And then finally, in this problem at least, we don't have to regroup in the hundreds place because we're not adding any hundreds. We have 1 100 we started with. We got an additional 1 100 by regrouping the tens. So we simply have 1 plus 1 or 2 hundreds. Okay. So every step that is carried out in the model has a corresponding step over in the algorithm. So again, the idea is that if students have been using these chip models throughout their conversations about place value, then these steps, they'll be adept at something like this, because really all this takes is organization within place values and then regrouping, and they'll be able to replicate those steps over on the algorithm. Okay, Subtraction can be handled similarly, meaning with a chip model. However, since subtraction is a different operation than addition, obviously, the steps that we're going to carry out are going to be slightly different. Okay? So the first thing we want to think of, let's just think of an example, maybe 35 minus 12. Now, in a couple of clips from now, we're going to talk about subtraction as an operation. And one of the ways we can interpret subtraction is with a takeaway interpretation, meaning we would think maybe of 35 minus 12 as taking 12 away from 35. Now, we're not going to be able to actually physically do that on the board, so what we can do instead is to illustrate taking 12 away by crossing out 12 chips starting with 35. So that's what we're going to do on our algorithm. We're going to cross out 12 chips. We're going to start with 35. So the kind of skeleton of the model is going to look much the same as it did before. But again, since now we are subtracting, we just start with the 35, which is our 3 10s and 5 1s, and now we're going to illustrate taking away 12 from 35, meaning we're going to cross out 12. Well, what does it mean to cross out 12? It means to cross out 1 10 and 2 1s. Again, one of the key features of the subtraction algorithm is illustrated very clearly in that we're going to subtract within place values, just like we added within place values, meaning we're going to take 2 1s away from 5 1s. We're going to take 1 10 away from 3 10s. With a problem like this, a relatively simple problem, there's no regrouping involved. We can take 2 1s away from 5 1s, right? I have enough 1s to cross off 2 of them. I can take 1 10 away from 3 10s. I can cross off 1 10. And we see that the steps that I did here, there certainly weren't very many of them, but they can be replicated on the algorithm as well. Right? What did we do? We simply took 2 away from 5, and we simply took 1 away from 3 to get our answer of 23. Okay, so again, the first kind of main feature of the subtraction algorithm is really the same as it was with addition. We subtract within individual place values. Again, as with addition, we see that more complicated problems arise when we actually have regrouping involved. So let's do a subtraction problem where we have some regrouping. So let's say we wish to subtract 312 minus 145. Again, if we were teaching this to a class of students, we would do probably several examples on the model first before we dove right into the algorithm. I'm going to do the 2 problems in tandem, again to illustrate how a step on the model can be replicated on the algorithm. Again, in this case, we have 3-digit numbers that we're subtracting, so our chip model needs 3 columns, 1s place, 10s place, 100s place. Again, we remember also that subtraction, one way of thinking about subtraction is taking away, so we're going to think of this as taking away 145 from 312. So we're going to start with 312 on our model and take 145 away. 312, or 312 I should say, 300s, 110, 2 1s, and now we need to take away 145. As we saw last time, we're going to represent this with crossing out 145. 145, though in expanded form, is 1 100, 4 10s, and 5 1s. So last time we proceeded by trying to just take away the 1s, but we notice now we have a problem. We only have 2 1s that we started with, but we need to take away or cross out 5 1s. Okay? So just like with these kind of second stage of addition problems, this is when place value kicks in. Now, if our place value rule in base 10 is 10 of one denomination makes 1 of the next higher denomination, we can also run that backward and say that 1 of an individual denomination is equivalent to 10 of the next lower denomination. What that means is we can get more 1s by breaking up 110. And we're going to illustrate this in kind of the opposite way we illustrated regrouping with addition. We are going to grab onto this 10 and illustrate that it can be split up into 10 1s. By doing so, now we have plenty of 1s, right? We need to cross out 5 1s. We have plenty of 1s we can cross out now. So we can illustrate subtracting off 5 1s by crossing off 5 of the 1s chips. And that's the first step in the computation. Again, what we would like our students to see is that we don't really need chips to do this. We can just think to ourselves, what did we actually do here, and replicate that on the more efficient algorithm. So what did we actually do here? we realized that we need to subtract within place value, so we would try to first take 5 away from 2. We realized we cannot do that, so we need to get more 1s. Where do we get 1s? We can get 1s from this 10. So what we are doing, what we did on the model, is we broke this 110 into 10 1s. That's the same thing we're going to do here. What ends up happening? The number of 10s that we started with is going to decrease by 1. Right? Because we're taking one of those 10s, we're breaking it into 10 1s. So this 10, we started with 110, but that number is going to reduce by 1, and now we're going to be left with 0 10s. What happened to the number of 1s we had? We started with 2, but by breaking up 110 into 10 1s, we got 10 more 1s. Now, oftentimes, at least the way I learned it, we just stuck a little 1 right here, but I think that kind of misses the point of what's happening. So what I like to do is just cross this 2 out and illustrate what's actually happening here. The number of 1s increased by 10. It went from 2 to 12. Okay. Now that we have 12 1s, we can certainly take 5 away from 12, and that's where our 7 1s comes from in the answer. And again, once we understand how one of these steps is carried out, we just replicate this as many times as we need to. So in the tens place, on the model, we need to, because remember, we're subtracting 145. 1 100, 4 tens, and 5 1s. We've already taken care of the 5 1s. We now need to subtract 4 tens. We don't have any 10s to cross out, though, right? So just like before, we need to get some more 10s. Using our place value rule, 1 100 is equivalent to 10 tens. We can illustrate that on the model. And then now we have plenty of 10s. We can certainly cross out 4 of them to illustrate subtracting off 4 tens. Over on the algorithm, we just replicate exactly what we did on the model. So on the algorithm, we think to ourselves, well, I need to take away 4 tens, but I don't have any 10s to take anything away from. Where I can get 10s is from a 100. So I'm going to take one of my original 3 100s, and I'm going to break that 100 into 10 tens. So the number of hundreds that I began with is going to reduce by 1, because I took one of them and reduced it and made it into 10 tens. What's going to happen to the number of tens? It's going to increase by 10, because 1 100 is the same as 10 tens. Now, at this stage, I have 0 tens. I need to add 10 to that. So now I'm going to have 10 tens. And now I can carry out the subtraction of 10 minus 4 to obtain 6 tens. In this problem, at least, there's no more regrouping, because all I have to do is subtract 1 100. I can illustrate that by crossing out. Here on the algorithm, we would realize, again, there's no need for regrouping. I can subtract 2 minus 1, and that's where my answer of 167 comes from. So again, as we did with the addition algorithm, every step on a chip model translates to a corresponding step on the algorithm. Of course, we don't want our students subtracting in later grades with chip models. They're very cumbersome. And imagine how you would, how large a chip model would be needed for subtraction of 5-digit, 6-digit, 7-digit numbers, right? The algorithm is the most efficient way of subtracting or adding or multiplying or dividing for that matter. So we hope that a model motivates the steps so the steps make sense to students, and they will not have to rely solely on memorization. They'll be able to figure out what the correct steps are.